Now let's look at the famous n-queens problem. This is a classical problem used to illustrate recursion. It's also a very hard problem. So in fact, for me, before I started teaching competitive programming, I don't think I really have uh, ever written a n-queens solution in a procedure language. So it's easier to do it in some of the other like functional programming language, or I also used the logic programming language Prolog before, so it's easy to do it in those languages. But um, I think actually I would have struggled if I asked to write the n-queens in Java. So the problem is we want to place n queens in chess on n by n chessboard so that no two queens attack each other. So each queen will attack the whole row it's in, the whole column is in, and also the two diagonals. So this particular problem asks to compute all the distinct solutions. So for every solution, you actually generate a board and then return that. And n-queens 2 on LeetCode just asks for the number of configurations. But the basic idea is the same. It's just that in the end, whether it's simply you add a counter or you actually reconstruct the state that you have maintained. So the key question is how do you maintain the state of the board? So the basic recursion idea is straightforward, right? So you can place one queen and then you try to place the next, and you try all possible position and then you go to the next. After you place your last queen, then you're done. The question is how to represent the board. The maybe the most straightforward representation is you well, there are multiple implementation. Well, one way is let's say we remember the XY coordinate of every queen, so that's one way to do it. But then when we place a queen, then we have to sort of check with every other queen to see whether they are attacking each other. Um, so yeah, so that's one solution. But I think uh, it's perfectly doable. It's just that it the code may be the code will be more complicated than a better solution, and also may take longer. Another solution is every board I can use say 1 and 0, a boolean, to represent whether there is a queen or not. So then every time if I place a queen, then I need to scan through the board to see whether there's another queen that they did, so that they attack each other. So that may be the worst board representation, at least in terms of time, because you need to scan the whole board to check whether you can place a queen in a particular position. So the question is, can we do better? And the answer, of course, is yes. Whenever we ask a question, or whenever I ask a question, can we do better? The answer is always yes. Otherwise, I wouldn't ask that question. So we can take advantage of some of the constraints to use that to make the state representation more succinct. So because we know every queen can only be placed in, there can be at most there should be exactly one queen on each row. So because we have n rows, we have n queens, and no two queens can occupy the same row. So then we can call that the queen 1 through n, that each of the queens are always in the row of its number. Then the only state is which column the queen is in. So then the state can be represented by a size n integer array, which stores the column number of the row of the queen that are at row I. So that turns out to be a better representation than the solution, than the two other approaches that we explored earlier. So then we need to check when a new queen, we try to place a new queen, whether it will attack another queen. So we need to check. So checking column is easy, right? So it's just comparing. Checking diagonal is a little bit trickier. So once you figure that out, then essentially the whole thing is done. So here, I first show the Java code for nqueens 2, counting the number of ways of placing nqueens. So this is the recursive part. This is the recursive part. So this is our state is a int array, and I said we're trying to place the queen on row I, and the base condition is if I is n, that means we already placed the queen from row 0 to n-1, then we're done. So then that means we succeeded. So we just increment the counter and then return. Otherwise, we will do a double loop. The first loop is to try all possible positions to place the queen on row I. So J loops through all possible rows. And inside, we are checking whether it's okay to place the queen on row I in the jth row. So if it's okay, we do the assignment, and then we recursively call this again. So this loop checks that condition. So we need to check three things. We need to check whether there's another queen in the same column. So that's easy to check. We loop through all of this, and then we will simply check whether this another queen is already so for another queen that's already placed, whether it's in the same row column number, also column number J. So if that is the case, then it's not going to work. We want to try the next position. So we want to jump through this. I want to exit this for loop, this inner for loop. I also want to jump across this code of trying this position, using this position to do recursive call. So here I use this labeled loop and then continue the outer loop. So that's one condition. We also need to check the diagonal. So the logic for checking diagonal is it's maybe a little bit tricky, and I don't think I don't have really very good succinct explanations. I think it's maybe you take a board, you place it, and then you can see. Essentially, we are checking whether they're diagonal. Is essentially whether the two points form a 45 degree line or 135 degree line. So either x2 minus x1 equals y2 minus y1 or equals negative y2 minus. So that's basically what we are doing here. So yeah, if look at the board, then we have the queen I and then the position. So essentially we're checking that whether they are on the same line, either this direction or this direction, and that's what that code does. So the driver is straightforward. Just call the recursive call. Yeah, so create the array that will be holding the position, and then call it, and then that's it. So this C++ code is actually solving nqueens. We are actually constructing the board, but I don't think I don't think the constructing code is here. So this is similar to, no, it is here. So this is the base case. When I reaches n, then that means we've already find a solution. So we create a vector of string to represent the board, and then just go through the position where we have queen, and then we put Q there. And I think this line is just representing an empty line, empty row. And here the logic is exactly the same. It's just that instead of using the continue outer loop or using a goto statement, I use a Boolean variable to store whether there is a conflict.
So when we find the conflict, we will set that and then break, and then in that case, then we can skip this using this position.